The final thing we're going to do, thinking about binding neutral molecules and to begin to move us onto the next stage of our screencasts, is to think about how cyclodextrins and supramolecular interactions can organise physical matter, something that you can actually see that's controlled by non-covalent interactions. This is very cool. This is work from Akira Harada in Osaka in Japan, and there is amazing work in supramolecular chemistry done in Japan. It's a real powerhouse of the subject. Also in China, there's incredible work going on in supramolecular chemistry. So, the idea of this study is that selective supramolecular interactions can organise physical matter. And by physical matter, I mean something that you can touch. What's the strategy? This represents a polymer. And to the polymer is attached, it's a bit hard to see in here, but there'll be a better image included, an N-butyl chain. And this is a polymer, and attached to this polymer is an alpha cyclodextrin, the small one of the three bears. And the N-butyl chain fits nicely inside the alpha cyclodextrin. There is size selective binding. There's then a polymer, and to this polymer is attached, and it really is hard to see there, easier to see on your own version, a tertiary butyl chain. Big, umbrella shaped. And that means it prefers to bind to a polymer that has a beta cyclodextrin attached, a larger cavity, the medium of our three bears. So the tertiary butyl sits in beta cyclodextrin, the N-butyl sits in alpha cyclodextrin. And that's because the T-butyl is sterically demanding, so it needs the beta cyclodextrin. Now, these polymers that they're working with were gels. Okay? So the polymers were gels. And what Harada did that was really clever and visual was he stained them all a different colour. So one was yellow, one was blue, one was green, and so on. So all four were different colours. So you could see with your naked eye which was which. And then what he did is he took those four polymers and put them down in a petri dish of water. There's the beta cyclodextrin one, the alpha cyclodextrin one, the N-butyl one, and the T-butyl one. And what he hoped is when he shook the petri dish of water, the beta cyclodextrin one would go and interact with the tertiary butyl gel. And the alpha cyclodextrin one would go and interact with the N-butyl gel. And they would find their ideal partners. And from this complex mixture, they would stick together in pairs of different colours. Here's the picture that showed that it worked. The alpha CD and N-butyl gel aggregated together, and the beta CD and the T-butyl gel aggregated together. Chunks of gel being glued together by individual molecular scale interactions that are size selective in nature. So the interfaces are being controlled by molecules of these blocks of gel. It's very cool that molecular scale interactions were selectively holding together visible objects. And this expresses something that's really exciting about supramolecular chemistry. Can we, by understanding interactions between molecules, begin to build the world around us? Even better, can we allow that world to spontaneously emerge because of the way we've programmed the molecular structures of the different bits? This begins to introduce the concept of self-assembly, the idea that the world can organize itself based on the information programmed into individual molecules.